Chapter 7 is on systems of equations, and hopefully that sounds somewhat familiar because we talked about systems of equations last year. Do you remember what a system of equations is? A system of equations is when, so I'll just define this here, it's when two or more equations are considered together. Okay, so for example, here's a system of equations right here. And when I say they're considered together, it means when you're solving this system of equations here, you're trying to find one x value that would go here, and one y value that would go there and would go there, so that both of these equations are satisfied, right? So that it works in both of these equations. And we did that last year. We did it in 3 different ways solving them. We solved by graphing, and that's what we're going to do today. We are going to do graphing. Too many colors, this is ridiculous. We're going to do graphing today, and other ways we solve systems equations were substitution and also elimination, and we will work with substitution next day. But today what we're doing is we're graphing, and you'll notice what we're doing today is we're going to concentrate on nonlinear systems of equations. So what if we're working on nonlinear systems of equations, we better figure out first what's a linear system of equations. Linear system. Well, a linear system is, as you can probably guess, it's a system equation where when you graph the two equations, they're both lines. Another way you can say that is both equations are first degree. Remember degree? We've talked about it a little bit in this class. Both these equations in the example here are first degree because there's no exponents on the variables. There's no y squareds or x squareds or anything like that. And that's why when we get to parabolas, quadratics, right, what we did for half this course practically, those are second degree because in a parabola, of course, you have an x squared. So that's a second degree. But linear systems have both of them degree 1. In other words, they're both lines. And this is totally exactly what we did last year. This is just a quick review. So let's do this first question pretty quickly. There's 2 lines here, and we're going to graph them all, and we're going to figure out which x value and which y value would solve both these equations. So the first line here, we should probably graph this one by using slope-intercept form. I'm not going to spend time on that. You should go back and watch the video if you don't know how to do that. But basically, the y-intercept's at -4. And then we want to rise to, this is the slope, right? Rise to and run 3. Rise to, run 3. I could do that a couple times. 1, 2, 3. Maybe one more. 1, 2, 1, 2, 3. And then we're going to join that with a line. And I will extend it the other way. This takes a little while, but there we go. There's the first line. I guess we might want to put some arrows on the end of that line. Great. For the second line, there's different ways we could graph this. One way you could do is you could look for x-intercepts and y-intercepts. So if I'm looking for the x-intercept, make the y 0. So you have x equals 6. Oh, that was easy to find that one. And if you're looking for the y-intercept, make x 0. So that would leave you with -3y equals 6 or y equals -2, right? Divide both sides by -3, you get y equals -2. So there's the y-intercept there. And then we could graph that line. And that's fine. We don't need to do different colors or anything, do we? So this is the second line, goes like this. And again, I'll extend it. This must be a little painful to watch, but and we could put some arrows on the end of that one as well. Okay, so all the points in this line here, point, there's an infinite number of points in that line, and they all satisfy this equation. Too many colors here. Here, they all satisfy, this green line satisfies that green one there. And all the points on this line all satisfy this equation. So is there any point that satisfies the green one and the pinky one? Yes, there is. It's this one right here. The point is 6, 0. So in other words, the answer to this system of equations must be 6, 0. Not sure if it's true. Let's try it. Let's put it in the second one here. 6 take away 3 times 0 is 6. That's true. 6 take away 0 is 6. Good. Let's try the top one. If you put 6 in here, you get 2 times 6 is 12, divided by 3 is 4. So 4 take away 4 is 0, and that would be a 0 right there, so it works. They both work. Yep, it's the only point that works in both of them, satisfies both the equations. Alright, so that was last year. Now what we're going to do is nonlinear system, and basically it's very similar. The only difference is a nonlinear system is if any of the equations are not first degree. Well, they could be second degree or third degree or etc., etc., but guess what we're going to have? Second degree, because we're going to look at quadratics. So you got two cases we're going to look at this year. We're going to look at linear quadratics and quadratic quadratic. Linear quadratic is when you have one line and one parabola. So what are the possibilities? Like how many solutions could you have? Well, let's think of this here. Could you have no solution? Yeah, you could have no solution. What if I think we've talked about this. If your parabola looked like that and your line looked like that, there's no point of intersection. There is no solution. Could you have one? Yep, you could have one solution. What if your parabola was like that and your line was like that? Doesn't need to be the vertex, by the way. That would be one solution. Any other possibilities? Yep, you could have two solutions. Parabola, these aren't very good parabolas I'm drawing. Something like that. You now have two solutions. Any other possibilities? No. So for linear quadratic, there can be 0, 1, or 2 solutions. How about quadratic? How about quadratic? Two parabolas. Why don't you stop this video and see if you can figure out how many there could be. Could there be 0? Did you stop it? Don't let me do it. You try it. Could there be 0? Yes. Never touch each other. Could there be 1? Sure. Where are they going to touch? Vertex. Good. Could there be 2? Uh-huh. Could there be 3? No. So is that it? No. There's one other possibility. What's the other possibility? You figured out why I put in these points here. The other possibility is you have one parabola, and then you have the equation of the other parabola, and when you graph the other parabola, it's right on top. It's exactly the same parabola. How many solutions are there? Infinite. So for quadratic, there can be 0, 1, 2, or infinite solutions. So I guess this here was 0, and this was 0, and this was 1, and this was 1, and this was 2, and this was 2, and this was infinite. Alright, that was quick. Hopefully that makes sense. Let's go on to some questions. Is 2, negative 3 a solution to the following system? So what we're asking is, do these points, this x value and this y value, do they satisfy both of these equations? Well, let's try the top one. That would be 3 times 2 take away negative 3 equals 9. Is that true? 6 take away negative is the same as plus 3 equals 9. That works. So can we already say that yes, it is a solution? Not yet. It has to work in the second one as well. So let's try the second one. X squared, well that is 2 squared plus negative 3 equals 7. Or 4 plus negative 3 equals 7. Is that true? No. So is 2, negative 3 a solution to the following system? No. It is not. Alright, let's go on here. So now we're going to solve a couple systems, and we're going to do it by graphing. Next class we'll start doing it without graphing, and that'll be nice because graphing takes a long time. But we do need to know how to do this. Alright, so what we're going to do is we're going to graph both of these things and then see where the intersection points are. So the first is a quadratic, and the second one is linear. Alright, so we're going to have a parabola and a line. Y equals x squared minus 5x plus 4. Oh, it's not even in standard form. So we have to figure out the vertex. How are we going to do that? How about negative b over 2a? So that's negative 5 over, what? What kind of horrible parabola is this going to be? It's going to be decimals. I hate this. 2 times 1, which ends up being 5 over 2, or 2.5. And now, we need to plug that into the x's. I really don't want to do this. Why did I put this example here? Y equals 2.5 squared minus 5 times 2.5 plus 4. I don't even know if it fits on the graph. I hope so. 2.5 squared is 6.25, as you all know. And 5 times 2.5 is 12.5, and then plus 4. What? Oh, why did I do this example? It's horrible. So I have minus 6.25 plus 4, negative 2.25. What was I thinking when I did this? This is horrible. The vertex is 2.5, 2.5, and negative 2.25. I have no idea why I did this. I'm sorry. What else can we do? I guess we could do the y-intercept. To get the y-intercept, we put zeros into the x's, so that's easy. 0 here, 0 here, we get a y-intercept of 4. And if we have that point, that was over half, 1, 2. We can go another half, 1, 2, and it would be the same spot. Hopefully that makes sense. I'm sorry, this is really, really a bad example I've used. I guess we should get another point. I don't know. Let's see what happens when we put 4 in there. If I put 4 in there, I get 16 minus 20. Oh, wow, this is nice. Equals negative 4 plus 4. Oh, I just, basically what I'm doing here is I'm making a table of values. I'm going to put some values in there. And since I'm at 2.5 here, I decided I'd use 4 and maybe 3. So if I put 4 in there, I get 4 squared, which is 16, minus 20 plus 4, and that gives me 0. So that's very nice. I get here, and then so I guess I would also get here a point. And if I put 3 in there, I get 3 squared is 9, minus 15 plus 4 is negative 6 plus 4 equals negative 2. So here and here. So this is my parabola. I'll try to do my best so you don't have to do parabolas with crazy vertices like that. But anyway, it gives us a sense. This doesn't look very good. All right, now let's graph the second one, the line here. We could do that with a using x-intercepts and y-intercept. If I'm looking for the x-intercept, that is when y equals 0, so that just leaves us with x equals 1. Oh, what do you know? I've already found one of the intercepts. If I'm looking for the y-intercept, that would be when x equals 0, so I would have negative y equals 1, which means y equals negative 1. So right here. So basically, this is just a line that's like at a 45-degree angle. It is like this. And you can see that it's gone through 2 points there. I don't need to extend it, but I will. Okay, and when we do these, I'll make sure that you always get whole number, or yeah, I think I'll always make sure you get whole number answers when you graph, so you don't have to worry about if it's 1.2 or 1. Yeah, this is the point right here where they cross, and this is the point right there where they cross. So what are those 2 points? Well, this point here is 1, 0, and this point here is 5, 4. So those are the 2 solutions to this question. If you're not certain, you don't trust yourself, try plugging the 1, 0 in here, and it'll work. Try plugging 1, 0 in the bottom one, it'll work. 5, 4 in the top one works. 5, 4 in the bottom, it'll work in all of them. Okay, the last example is a quadratic. You got to draw 2 parabolas. Thankfully, they're both in standard form. Unfortunately, I've done another one with fractions. Mr. Wadge, you're really cruel. All right, the first one's pretty quick. Its vertex is at 2, 3, right? If you don't remember how to graph parabolas, go look at a different video. I'm not going to spend a lot of time with it today. I'm going to use the step pattern. So since it's negative, it's the same as negative 1. I'm going to go over 1, down 1, and then over 1, down 3, and then over 1, down 5. 1, 2, 3, 4, 5. Same on the other side. We go here, we go here, we go here. I wish they had a parabola making feature on this thing and I wouldn't have to embarrass myself by trying to draw these. It's really not good. Alright, now the second one, where's the, I'll do it red. Where is the vertex? It's at 1/2, 3 halves. 1/2, so that's about here, and 3/2 is 1.5. 1.5. So it's right around here. I don't know if that's supposed to be the actual, no, I don't think that's supposed to intersect. No. Okay, and then it's 2. So if I do step pattern, I'm going to go over 1, which would be all the way to here, and then I would go up 2. 1, 2, so it would be right there. And then I'd go over 1, so it'd be here, and I'd go up 6. 1, 2, 3, 4, 5, 6. Now, I imagine some of you are like really confused by that. So I will fill in the other side here. Over 1 up to here. Over 1 up to here. But I'll also do the table just in case you have no idea how I did that. So my vertex was at 1/2. Why don't we pick the numbers 1, 2, 1 and 2. I think that'll be good enough. So if we put 1 in here, I got 1 take away a half, which is a half. A half squared is a quarter. 2 times a quarter is 2 quarters, plus 3 over 2. But 2 quarters is the same as a half, isn't it? So really what we have is 1/2 plus 3 halves, which is 4 halves. 4 halves, that's the same as 2. So the point is 1, 2. 1, 2. Hey, what do you know? We just found our point right there. If we have that point, we must also have that point there. What the heck? Let's figure out this other point just for kicks. 2 take away a half is 1.5, and 1.5 is the same as 3 over 2, right? Then we're going to square it, so you get 9 over 4. Then you're going to multiply it by 2, and when you multiply it by 2, you could simplify this, so make it 1 and 2. So you now have 9 over 2, and you're adding it to 3 over 2, which gives you 12 over 2, and 12 over 2 is the same as 6. So you should have more points at 2, 6. 2, 6. That makes sense? I hope so. And so there'll also be one there. Wow, look at all the wonderful points we now have for this parabola. And still I can't draw it well. Oh, it's horrible. But you can see that the one point they both share is right there. There's only one solution in this case, and the solution is 1, 2. And again, not sure if that's right or not. No, it's really hard to read. Not sure if that's right. Put 1 in here and 2 in here, and it will work. Put 1 in here, 2 in here, and it will work. Yeah, I think that just about covers it. All right, so have fun drawing lines and drawing more parabolas. If you remember how to draw lines and draw parabolas, and you just definitely should, we spent chapters on it, this should be a very doable section. Won't you come closer to me, baby? Hey. Now you already got me.